200 seconds. That is how long a single machine sitting in a quiet laboratory in California needed to finish one calculation. Handed to the finest ordinary supercomputer on Earth, that same calculation would still be running 10,000 years from now. But the speed is not the strange part. The strange part, the part that has quietly unsettled some serious physicists, is that nobody who built the machine can tell you where the calculation actually happened. Not inside the chip, not anywhere you could point to in the room, possibly not anywhere in the universe you can see. By the end of tonight, you're going to understand exactly what that means, and why it suggests the world is not built the way your eyes insist it is. So if the answer is not in the machine, and not anywhere in the room, then where exactly is the thinking happening? Get comfortable and settle in. If you have not subscribed yet, go ahead and subscribe so the next quiet journey through the strange edges of reality finds its way to you. Stay with me, because the trail runs through a satellite, a vanished genius, and a room colder than the space between the galaxies before it comes home to you. Let's get into it. Part 1. The Machine That Shouldn't Work. In October of 2019, in a laboratory in Santa Barbara, California, a machine finished a calculation in 200 seconds. That same calculation, handed to the most powerful ordinary supercomputer on Earth, would still be running 10,000 years from now. Not 10 years, not 100, 10,000 years, a span longer than all of recorded human history, from the first marks pressed into wet clay to the phone sitting beside you right now, folded down into the time it takes to soft-boil an egg. And here is the part almost nobody says out loud. The strangest thing about that machine is not the speed. The strangest thing is that nobody can quite tell you where the calculation happened. I want you to sit with that, because we are going to spend the next couple of hours following it all the way down, patiently, one careful step at a time, and where it leads is not a story about faster computers, it is a story about the world, about what the world is actually made of underneath the version your eyes hand you. By the end of tonight, I think you will come away with a quiet suspicion that has been creeping up on some of the most serious physicists alive, and it is this: the world is not where you think it is. Hold on to that sentence. It is going to come back at the very end, and it is going to mean something much larger than it does right now. The machine was called Sycamore, built by the quantum hardware team at Google, and it carried 53 of something called qubits. We will spend real time on what a qubit is, because that is where the mystery lives, but for the moment just hold the number. 53. The task it ran had a dry, almost boring name: random circuit sampling. You run a series of randomly chosen operations, and then you measure what comes out. It was designed to be a benchmark, a way of asking a machine, in effect, can you do something that ordinary physics running on ordinary matter simply cannot keep up with? And the answer that came back was yes. Google published the result, dropped it into the scientific literature like a stone into a still pond, and the ripples have not stopped since. Now, to be fair, and we are always going to be fair in this story, because the honest version is stranger than the hyped one, the company IBM pushed back almost immediately. Their engineers looked at that 10,000-year figure and said, hold on, with a cleverer classical approach and enough hard drive storage, you could probably simulate that same circuit in something more like 2.5 days. And they were not wrong to say it. The back and forth that followed, two teams of brilliant people arguing about exactly how impossible the impossible thing was, is one of the more entertaining chapters in recent physics. But notice what both sides quietly agreed on, even while they argued. Nobody claimed that an ordinary computer actually matched the quantum machine at this task. They were arguing about the size of the gap, not about whether the gap was real. And the gap was real. What Google had shown, for the first time, was a machine doing a computation for which there is no efficient ordinary explanation. Not a slow one that could be sped up, not an approximate one that could be sharpened. A concrete, measurable case of a machine doing something that matter, following the ordinary rules, should not be able to do in any practical sense. Then, 5 years later, in December of 2024, the same team announced a second chip. They called it Willow, and it carried 105 qubits, and it did something that, if anything, is even harder to explain than raw speed. To understand why it matters, you have to understand a rule that has held for every machine human beings have ever built. The rule is that complexity means fragility. Your car has more parts than your bicycle, and it breaks down in more ways. A power grid has more ways to fail than a single generator. A body has more ways to go wrong than a single cell. The more pieces you add to a system, the more ways that system can fall apart. That is not bad engineering. That is the ordinary tendency of the universe, the slow pull of things toward disorder, expressing itself through every device we have ever made. More parts, more fragility. That is the rule. Willow broke the rule. As the team increased the number of qubits used to protect a single unit of quantum information, the error rate did not hold steady, and it did not climb. It fell. It fell faster and faster the more components they added. The machine got more reliable as it got bigger. Every engineering instinct we have says that should be impossible, and yet there it was, measured, published, and confirmed. A system that stabilizes as it grows, a thing that gets stronger the more of it there is. So we have two facts sitting on the table, and I want to name them clearly before we go anywhere else, because everything tonight grows out of the gap between them and our ability to explain them. Fact 1, a machine performed a computation that has no efficient ordinary explanation. Fact 2, that same family of machines becomes more stable, not less, as it scales up. We can describe, with beautiful precision, how to build these machines, how to cool them, how to program them, how to read their answers. What we cannot do, what nobody on Earth can fully do with confidence, is point at a physical place and say, there, that is where the computing is happening. That is the part of reality doing the work. That is the resource being spent. The machine works. That is not the mystery. The mystery is why. And that mystery, it turns out, is not really about computers at all. It is about a quiet assumption every one of us carries around all day long without ever noticing it. The assumption that the world is made of separate things, sitting in separate places, with real empty distance in between. That here is here, and there is there, and the two are genuinely apart. It feels less like an assumption, and more like the most obvious fact there is. You are in one place. The far wall is in another. The nearest star is very far away indeed. Separation feels like the bedrock of everything. What these machines are quietly suggesting, and what we're going to build toward together tonight, is that separation might not be the bedrock at all. It might be a surface, a kind of smooth skin the universe shows to creatures our size, and underneath that skin the world may be stitched together in a way that has almost nothing to do with the distances we see. If that is true, then a machine that reaches under the skin, into the layer where separation stops meaning what we think it means, would be able to do exactly the things these machines do. It would compute in a space bigger than the one it sits in. It would draw on resources that are not bound to its own little cold body, and it would get stronger, not weaker, as it grew, because the thing it was protecting would not live in the fragile local world where things break. That is the road ahead. We're going to start with the coldest place in the known universe, a place human beings built on purpose, and we're going to work our way down through the arithmetic, through a satellite that should have made more headlines than it did, through a paper written 40 years ago by a man everyone ignored, and finally to the edge of a question so large that no one alive can answer it. Somewhere in there, the sentence I asked you to hold is going to come back around. The world is not where you think it is. Let us find out what that could possibly mean. Part 2. The coldest place we ever built. To understand these machines, you have to go and stand next to one, and standing next to one is a genuinely strange experience, so let me take you there. Picture yourself walking into the room where one of these processors lives. You might expect something like a server, a black box with blinking lights, humming quietly on a rack. That is not what you find. What you find looks more like a chandelier designed by someone who took a wrong turn into a fever dream. It hangs from the ceiling, a series of gleaming gold-plated stages stacked one below the other, each one smaller than the last, wrapped in copper and shielding, with cables running down through it like nerves carrying signals into the cold. The whole thing hangs inside a sealed chamber, and at the very bottom, smaller than a coin, sits the chip. Everything above it, all that gold, all that engineering, exists to do one thing: to make the bottom colder than almost anywhere else in existence. The device is called a dilution refrigerator, and the temperatures it reaches are difficult to hold in your head. The chip operates at around 20 millikelvin. That is 20,000ths of a single degree above absolute zero. Absolute zero is the temperature at which all thermal motion in matter theoretically stops, the true floor of cold, and it sits at minus 273.15 degrees on the Celsius scale. Now, To feel how cold 20 millikelvin really is, you need something to compare it to, so here is the comparison that gets me every time. Out in space, filling the entire universe in every direction, there is a faint background warmth left over from the birth of the cosmos, the cooled-down afterglow of the Big Bang itself. That background sits at about 2.7 Kelvin, and the chip at the bottom of that refrigerator runs more than 100 times colder than that. Let that settle. We have built, here on the warm surface of the Earth, a place colder than the average temperature of deep space, colder than the emptiness between the galaxies. One of the coldest places in the known universe is not out among the stars. It is in a laboratory, and we made it on purpose. The refrigerator cools in stages like descending through layers of winter that keep getting deeper. The outer shield sits at around 50 Kelvin. The next stage drops to about 4 Kelvin, then down to 800 millikelvin, then 100, and finally that operating floor of 20. Each stage is colder than the one above, and the whole assembly hangs in a vacuum, wrapped in gold-plated copper, because gold reflects heat and does not tarnish, and every stray whisper of warmth has to be kept away from the bottom. Now here is the question that unlocks everything. Why? Why go to all this trouble? Why build one of the coldest places in the universe just to run a computation? And the answer is the first real clue in our story, so I want to slow down and make sure it lands. The reason for all that cold is that the computation can only survive in near-perfect isolation from the ordinary world. The thing the machine is doing is so delicate, so easily destroyed, that it has to be sealed away from warmth, from vibration, from light, from almost every kind of contact with the reality around it. The machine, to put it plainly, has to be hidden from the world in order to work. Remember that sentence. It sounds like a simple engineering fact right now, a detail about cold and shielding. Much later tonight it is going to turn around and tell us something startling about the nature of reality itself. Let me take you all the way down to the chip to see what needs protecting. The qubits on these processors are built around something called a Josephson junction, and the idea is simpler than the name. Take two superconductors, materials that carry electricity with no resistance at all when they are cold enough, and separate them with an insulating layer so thin that it should stop the current cold. In the ordinary world, that gap would be a wall, but in the quantum world, pairs of electrons pass straight through the wall without ever going over it, a behavior called tunneling that has no equivalent in the world you and I move through. Cool these junctions down and drive them with carefully tuned microwave pulses, and they begin to behave like artificial atoms. They have distinct energy levels, they respond in controlled ways, and crucially, they can be placed into that fragile quantum condition we call superposition. Now, you have almost certainly heard the line that a qubit can be a 0 and a 1 at the same time, and that line is technically true and quietly misleading, so let me correct it, because the correction matters. A qubit in superposition is not like a spinning coin that is secretly already heads or tails, and simply hasn't been looked at yet. It is genuinely in a blend of both possibilities, described by something physicists call a probability amplitude. That is a number that carries two things at once. It carries how likely each outcome is, and it carries something called phase, which determines how different possibilities interfere with one another when they meet. And that word, interference, is not a side detail. It is the entire engine. Hold it lightly for now. We will build it up properly in a moment, but you can already feel why the cold has to be so total. A superposition is almost unbearably sensitive. A single stray photon of ordinary room temperature warmth landing on the chip can destroy it. A faint vibration carried through the floor from a truck passing on the road outside can destroy it. A wisp of electromagnetic interference from a cable or a phone can destroy it. Any of these causes what physicists call decoherence, the collapse of the delicate quantum condition into an ordinary one, and the moment that happens, the computation in progress is gone. This is why the refrigerators exist. This is why the gold shielding exists. This is why these laboratories are among the most carefully isolated environments human beings have ever constructed. You're trying to hold a pattern still, a pattern so faint that the universe itself seems to be constantly trying to rub it out. Let me set the scene one more time, gently, before we move on, because I want you to carry the image with you. Picture the room again, the soft rhythmic hum of the pumps, the golden tiers of the refrigerator hanging in the dim light like an upside-down cathedral, narrowing as they descend into the cold, the cables threading down through the stages like something alive, and at the very bottom, sheltered by all of it, that tiny chip, holding a pattern of possibility so fragile that a breath of warmth would erase it. Everything in that room, every degree of cold, every layer of gold, exists so that one delicate thing can hold still long enough to finish a thought. Let me hold you in that room a little longer, because there is a detail worth feeling. If you could somehow stand beside the chip at the bottom of the refrigerator, without your own body heat instantly ruining everything, you would be standing in the coldest place you had ever been, colder than the dark side of the moon, colder than the space between the stars, and it would be silent in a way that no natural place on Earth ever is, because there is almost nothing there to move, almost nothing to make a sound. The metal would be so cold that the very air, if there were any, would have frozen and fallen long ago. This is not a metaphorical stillness. It is the stillness of a place engineered to have as little happening in it as physically possible, because every little happening, every flicker of warmth or motion, is a threat. The chip sits in the middle of that manufactured nothingness like a held breath, and the reason for all of it, the reason for the gold and the vacuum and the layered cold and the silence, is to keep the world from touching the one fragile pattern the machine is trying to hold. Every defense in that room is a defense against contact, against the ordinary, warm, local reality pressing in and collapsing the delicate thing at the center. You're looking, in that cold silence, at a machine whose whole existence is organized around the single desperate task of not being touched by the world for just long enough to think one thought all the way through. A machine that has to be hidden from the world in order to think. It is a beautiful image, and it is a strange one, and it is our first hint that whatever these machines are really doing, they are not doing it in the ordinary warm world of solid separate objects. They are doing it somewhere else. And to find out where that somewhere is, we have to do a little arithmetic. Nothing hard, just some doubling and some honest counting, and that counting is going to lead us to a place where we quite literally run out of universe. Part 3. The arithmetic that runs out of universe. Let us do some mathematics together. I promise it will not hurt because it is nothing more complicated than multiplication and some honest bookkeeping. But I want to warn you gently in advance, because the most unsettling thing about quantum computing is not the hardware, and it is not the cold. It is the numbers. And the numbers, once you follow them all the way to the end, leave you standing in front of a conclusion that is very hard to walk back from. Start with an ordinary computer, the kind you're almost certainly holding or sitting near right now. It stores information in bits, and each bit is either a 0 or a 1. 2 bits can represent 4 possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. 3 bits can represent 8 combinations. Every bit you add doubles the number of possible arrangements. With 10 bits, you have 1,024 possible states. With 50 bits, you have more than 1 quadrillion. But here is the key thing about an ordinary computer. At any given instant, the machine is in exactly one of those states. It can move from one to the next, run through them one after another, but it only ever inhabits one at a time. One arrangement, then the next, then the next. That is what ordinary computing is. A quantum computer does something fundamentally different, and this is the hinge of the whole night. So let me lay it out slowly. A single qubit in superposition does not represent just a 0 or just a 1. It represents a blend of both. 2 qubits in superposition involve all 4 of the 2-bit combinations together. 3 qubits involve all 8. 10 qubits involve all 1,024 at once. 50 qubits are bound up with all 1 quadrillion combinations simultaneously. The system does not step through these arrangements one after another. It is entangled with all of them at the same time, and it produces its answer through the way all those possibilities interfere with each other. Now let us push the number and watch what happens. Take 300 qubits. 2 multiplied by itself 300 times comes out to roughly a 2, followed by 90 zeros. Write that out and it is a number that means almost nothing to the human mind, so let me give you something to measure it against. The total number of atoms in the entire observable universe, every atom in every star, every planet, every cloud of gas, out to the furthest edge we can see in any direction, is estimated at around 10 to the 80th power. That is a 1 followed by 80 zeros, and a 300-qubit processor, running in full superposition, would be bound up with a number of states that is not just larger than the number of atoms in the universe. It is larger by a factor of 10 billion. A machine the size of a fingernail, involving more distinct possibilities than there are atoms in everything that exists. 300 qubits, just 300. Willow, the machine we talked about earlier, already carries 105. IBM's roadmap points toward thousands within this decade. People talk seriously about machines with 1,000,000 qubits within our lifetimes, and the space of possibilities those machines would touch makes 300 look like a rounding error, makes it look like nothing. Now, this is the point where a careful person raises a hand, and it is a good objection, so let me take it seriously rather than talk over it. You might say, wait, the machine is not really storing all of those possibilities in the way that an ordinary memory stores data. Those probability amplitudes are not tiny physical objects sitting in tiny physical drawers somewhere inside the chip, and when you finally measure the thing, you only get one answer out, a single string of zeros and ones. So where is the paradox? Nothing was ever really stored. Here is the answer, and it is the crack through which everything else tonight is going to enter. The interference between all those possibilities demonstrably happens. The correct answer demonstrably emerges from a process that, if it had been an ordinary computation, would have required examining an astronomical number of possibilities in parallel. You cannot get the answers these machines produce from a process that was only ever in one arrangement at a time. The mathematics of how the output is created requires that the intermediate steps involve something operating across the entire blend of possibilities at once. So the question is not whether the system was, in some sense, working with all those states. The mathematics of quantum mechanics says that it was. The question is a different one, and it is a much harder one. Where? Where was all of that happening? What physical substrate was holding that information? What part of reality was doing the work? Because look at the accounting again. In a system of 300 qubits, the number of possibilities exceeds the number of atoms in the observable universe. You cannot store a 2 followed by 90 zeros worth of numbers inside a 10 followed by 80 zeros worth of atoms. The arithmetic simply does not fit. You run out of universe before you run out of states. Read that again, slowly, because it is one of the strangest true sentences I know. You run out of universe before you run out of states. Let me put the size of this in terms you can almost hold, because the numbers are so large they go numb, and I do not want them to go numb. 50 qubits already involve about 1 quadrillion possibilities. A quadrillion is 1,000 trillion. If you tried to count them 1 per second, you would need more than 30 million years. That is just 50 qubits. Now double the qubit count to 100, and you do not merely double the possibilities. You square the whole enormous pile and then some. By the time you reach a few hundred, the count sails past every physical thing you could ever use to keep track of it. There are not enough grains of sand on Earth. There are not enough atoms in the Earth. There are not enough atoms in the Sun, or the galaxy, or every galaxy we can see stacked together. And still the count keeps climbing, because each new qubit is another doubling, and doublings are merciless. This is why physicists do not describe a quantum computer's power as a matter of storing more. Storage runs out, the universe runs out. What the machine is doing cannot be a matter of holding all those possibilities somewhere inside itself, because there is no somewhere large enough, anywhere, to hold them. Physicists actually have a name for the mathematical space in which these quantum possibilities live. They call it Hilbert space, and in a very precise sense, Hilbert space is larger than physical space. This is not poetry, and it is not a metaphor I am reaching for to sound impressive. It is a plain mathematical fact that the space required to fully describe even a moderately sized quantum system has more dimensions than the 3 we move through. The computation, whatever else is true about it, is taking place in a space that is bigger than the universe we can see. So the question stands there, unavoidable, refusing to go away. Where is it happening? I want you to feel the size of this, not as a lecture but as something almost physical, because this is the moment the whole story stops being abstract. You have spent your entire life assuming that whatever a machine does, it does somewhere inside itself, in the wires, in the cold metal, in a place you could point to if you only had a small enough finger. That assumption feels unshakable. It is how objects work. And here, for the first time, that assumption fails, and it does not fail because of philosophy, or interpretation, or some clever argument. It fails on pure arithmetic. Just counting, just doubling, 300 times, 300 of something smaller than a speck, and already there is no room anywhere in the visible cosmos to hold what it is doing. Stay with that vertigo for a moment, because it points inward rather than outward. We are used to feeling small against the size of the universe, dwarfed by distances and ages we cannot picture. This is the opposite feeling. This is the smallest serious machine we have ever built somehow being too large for the universe to contain. The mystery has turned around and is looking back at us. And it means that whatever a quantum computer is really doing when it runs, it is not keeping the work in its own little cold body, because its own little cold body and the entire universe around it is not big enough. The information has, in the plainest possible sense, nowhere in space to be. No address. Remember that phrase too. No address. It is going to come back near the end of the night, and when it does, it is going to mean the exact opposite of a problem. But we are getting ahead of ourselves. If the information cannot fit in space, then maybe, just maybe, ordinary space was never the right place to look. And that suspicion leads us to a man who said exactly that, out loud, 40 years ago, and was almost completely ignored for it. Part 4. The man who said space was the wrong place to look. In 1985, a physicist at the University of Oxford named David Deutsch published a paper in the Proceedings of the Royal Society of London. It had a forbidding title, something about quantum theory and the universal quantum computer, and it is now considered one of the most important papers in the history of computing. It is also, for a long stretch of years, one of the most quietly ignored. Not because it was wrong, because it was right in a direction most physicists were simply not prepared to travel. Deutsch was staring at the same problem we just walked through together, the problem of where. He looked at the exponential resources a quantum computer would need, that impossible pile of possibilities we counted a moment ago, and he asked the blunt question. If the information cannot be stored in this universe, because the arithmetic says there is not enough universe to store it, then where is it? And he did not treat this as a soft, poetic, unanswerable riddle. He treated it as a hard physics question with a definite physical answer. His reasoning went like this. The computation demonstrably happens. The simultaneous handling of an astronomical number of possibilities demonstrably happens. That processing requires a physical home. And if the physical home cannot be the matter in our observable universe, because there is not enough of it, then the home must be somewhere else. I want to be very careful and very honest here, because this is exactly the kind of claim that gets flattened and oversold online, and the honest version is more interesting than the hyped one. The particular somewhere else that Deutsch reached for was the interpretation of quantum mechanics known as the many worlds picture. And the many worlds picture, at its core, is an answer to a decades-old puzzle called the measurement problem. So let me sketch it quickly, because you need the shape of it to understand why anyone would take it seriously. In standard quantum mechanics, a system in superposition evolves smoothly and predictably, following a precise equation, spreading out into a blend of possibilities. That part is not controversial. It is verified to extraordinary precision. But then, at the moment you measure it, the blend seems to vanish, and you get one definite outcome. All the other possibilities simply disappear. Physicists call this collapse. And the strange thing about collapse is that the equation that governs everything else says nothing about it. The equation does not describe the blend suddenly picking one answer. That collapse was added to the theory by hand, not because the mathematics demanded it, but because that is what we seem to see. Every time we look, we see one outcome, so collapse must happen. But the mathematics never says so. In 1957, a graduate student at Princeton named Hugh Everett III proposed a radical way out of this. What if, he asked, the equation is simply right? What if there is no collapse at all? What if, when a measurement happens, every possible outcome actually occurs, not one after another, not with one winning and the rest vanishing, but all of them, together, in separate branches of a single reality that never stops evolving? The measuring device, the laboratory, the scientist, the planet, everything splits into parallel versions, one for each outcome, and each version is entirely real, and each is unaware of the others because the branches do not interact. This is the many worlds interpretation, and when Everett first proposed it, it was received about as warmly as you might expect. The dominant voices of physics at the time held that you simply should not ask what is really happening between measurements. Everett's idea was pushed aside, and he left academic physics almost entirely, went to work on defense problems, and died in 1982, at the age of 51, never knowing that his idea would one day be taken more seriously than it ever was in his lifetime. There is something quietly sad and quietly instructive in Everett's story that is worth holding for a moment. Here was a young man who looked hard at the equation everyone else was using, noticed that it never actually says the collapse happens, and had the nerve to suggest that maybe the equation should simply be believed. For that, he was largely dismissed by the most powerful figures in his field, figures whose entire framework was built on the idea that you should not ask what is really happening between measurements. Everett did not fight for decades to defend his idea. He walked away from academic physics almost entirely, and the world lost whatever else he might have discovered. And then, slowly, long after he was gone, the idea he had been brushed aside for became one of the most seriously discussed frameworks in the foundations of physics, taken by many as not merely possible, but as arguably the most conservative reading of quantum mechanics, the one that adds nothing to the equation and simply takes it at its word. It is a reminder that the history of this subject is littered with ideas that were ignored not because they were wrong, but because they pointed somewhere people were not ready to go. Keep that in mind as we proceed, because the whole story tonight has that flavour, again and again. David Deutsch knew about Everett and took him with complete seriousness, not as one philosophical option among many, but as a literal picture of what quantum mechanics is describing. And when Deutsch analysed what a quantum computer would actually be doing, the many worlds picture did not merely fit the result. In his view, it was required by it. A quantum computation, in his analysis, is interference between parallel computations running side by side in parallel branches of reality. The reason the machine can handle an exponentially large problem is that the exponentially many pieces of work are distributed across exponentially many parallel realities, each doing a small share, with the interference between them producing the answer. You collect the result in your branch, but the labour, he argued, was done everywhere. Now, I am going to plant a flag here and be scrupulously fair, because we are going to come back to this at the end of the night and look at it properly. Deutsch's reading is bold, it is serious, it is held by real physicists, and it is one honest answer to our question of where. But it is an interpretation of quantum mechanics, not an experimental result. The machine does not come with a label telling you the many worlds picture is correct. It is one door among several, and I am going to insist on that all night, because the internet loves to tell you that quantum computers prove the multiverse, and that is a step further than the evidence goes. What is true, and what is remarkable enough on its own, is that a physicist looking hard at these machines in 1985 concluded that the information could not possibly be stored in ordinary space as we understand it, that the answer to where was, in some form, not here, not in the space you and I move through, and here is why I wanted you to meet Deutsch before we go on, even though we are setting his boldest claim aside for now. He put his finger on the real shape of the mystery. The information has no address in ordinary space. Whatever the ultimate explanation turns out to be, whether it is parallel branches or something none of us has thought of yet, the starting point is the same. The place we naturally look for the computation, the ordinary three-dimensional space of separate things sitting at separate locations, is the wrong place. It cannot be there. There is not enough of it, and it is not built the right way. So if space is the wrong place to look, we had better ask a harder question. We had better ask whether ordinary space, with its comfortable distances and its clean separations, was ever the true bedrock of reality in the first place. And to answer that, we do not need interpretation, and we do not need philosophy. We need experiments, real ones. Some of the most carefully done experiments in the entire history of science, experiments so decisive that they won a Nobel Prize. And what those experiments show is that the universe, at its deepest level, does not keep its distant pieces truly separate. The universe, in a precise and testable sense, does not compute locally. Part 5. The universe does not compute locally. If the information a quantum computer handles has nowhere in ordinary space to live, then the natural next question is whether ordinary space was ever the right place to look at all. And this is where our story reaches its true pivot, the hinge on which everything after it turns. Because for the last several decades, physicists have been quietly running experiments that answer this question, and the answer is not comforting, and it is not vague, and it is not a matter of interpretation. It has been measured again and again, and it has held up every single time. The story begins in 1935 with an argument, and the argument was started by Albert Einstein. Together with two colleagues, Boris Podolsky and Nathan Rosen, Einstein pointed at a feature of quantum mechanics that he found genuinely unacceptable. The theory seemed to allow what he called, with obvious distaste, spooky action at a distance. Take two particles, prepare them together so that their properties are linked, a condition we now call entanglement, and then carry them far apart. Quantum mechanics said that measuring one of them would instantly fix the state of the other, no matter how far away it had been taken. Einstein could not stomach this. He believed the theory had to be incomplete. Surely, he argued, the particles carried some hidden information with them, some local instructions written into them from the start that determined how each would behave when measured. In his picture, the spookiness was just our ignorance. The particles already knew what they were going to do. We simply did not have access to the note they were carrying. For nearly 30 years, this looked like a matter of taste, a philosophical disagreement with no way to settle it. Then, in 1964, an Irish physicist named John Stuart Bell did something extraordinary. He found a way to turn Einstein's intuition into a number you could actually test. Bell showed that if the particles really do carry local hidden instructions, written into them in advance, then the correlations between measurements on two distant entangled particles must obey a certain mathematical limit. There is a ceiling on how coordinated they can be, but quantum mechanics predicted that this ceiling would be broken. The two pictures, Einstein's hidden instructions and quantum mechanics, made different numerical predictions about what you would actually see in the laboratory. Bell had taken a philosophical argument and turned it into an experiment. Now someone just had to run it. They did, and they kept running it, more and more carefully, closing every possible loophole for the next 50 years. An early test came in 1972 from John Clauser and a collaborator, and it favoured quantum mechanics, but it had gaps that a determined skeptic could still slip through. In the early 1980s, a French physicist named Alain Aspect ran a far more careful series of experiments in Paris, closing the most important of those gaps, and again the results came down decisively against Einstein's hidden instructions. But the debate did not fully close until a landmark set of experiments in 2015, most famously one conducted by Ronald Hansen's group at Delft University in the Netherlands. These experiments closed the last loopholes at the same time, using entangled electrons separated by more than a kilometre, with the measurements made so fast that no signal travelling at the speed of light could possibly have passed between the two detectors before both measurements were complete. There was no room left for a hidden local story, and the result came back the same as always. Bell's limit was broken, decisively, with no exit remaining. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for this entire body of work. And the conclusion it establishes is not in serious dispute among physicists. It is one of the most solid results we have. Local hidden variable theories are ruled out. The particles do not carry pre-existing local answers. There is no deeper ordinary layer underneath quantum mechanics in which everything is quietly determined in advance. Einstein, on this particular point, one of the few in his life, was wrong. Now I have to be careful here, because this is a place where popular retellings often overreach, and the honest version matters. The breaking of Bell's limit does not mean that measuring one particle sends a signal to the other. It does not mean information travels faster than light. There is a firm result called the no-signalling theorem that says you cannot use entanglement to send a message instantly. You cannot pick up the phone this way. The correlations are real, but you cannot control them well enough to transmit anything through them. So relativity is safe. Nothing is racing between the particles, but something is happening, and it is stranger in its way than a signal would be. The two distant particles behave in a way that is more coordinated than any local story about the world could ever produce, and there is no messenger passing between them to arrange it. Something about the structure of reality produces matched outcomes at two separated places, and that something is not carried through the space between them. And so, we arrive at the sentence I want you to hold, the one that is the true centre of this entire night. The universe does not compute locally. The relationship between two distant entangled particles is not maintained by anything living in the gap between them. It is, in the most fundamental sense, non-local. Let me put you inside one of these experiments, because I think the plain fact of it is more powerful than any explanation. Imagine you are standing in the laboratory at Delft in 2015. In front of you is a long, cold corridor, and at each end sits a detector, more than a kilometre of quiet Dutch air between them. At each detector waits a single entangled electron holding its breath. A fast random choice, made at the very last possible instant, sets the question each detector will ask, so late that not even a beam of light could carry news of one choice to the other, Before both answers are locked in, you watch the measurements happen. The two results come back, and they are correlated, matched more tightly than any local account of the world could ever allow. And then it happens again, and again, run after run, past every reasonable doubt, past every statistical objection. The two ends of that corridor keep agreeing with each other, and nothing at all, crosses the space between them to arrange the agreement. No wire, no field, no signal in time. Stand there and feel it, because it is not a trick, and it is not an error, and it is not a matter of interpretation. It is a plain, stubborn, repeatable fact about the world you live in. Reality refuses to keep its distant pieces truly separate. You have spent your whole life inside the certainty that two things far apart are genuinely apart, that here is here and there is there, and the space between them is real and empty and dividing. This is the moment physics looks at you, with a straight face and a mountain of hard data behind it, and tells you that separation is not the whole truth, that the distance you trust so completely is, at the deepest level, not the barrier you think it is. And if that is true even for two lonely electrons in a corridor, then hold on, because it turns out to be true across distances that would stop your heart. Part 6. 1200 kilometers, and the connection held. It would be easy to dismiss what we just saw as a delicate laboratory curiosity, the kind of thing that only survives on a polished optical bench, in a shielded room, over a distance of a few meters, and falls apart the moment you take it out into the messy real world. That would be a comforting thought. It is also wrong, and in 2017 a satellite proved exactly how wrong, in a way that should have made far more headlines than it did. The satellite was Chinese, and it was named Micius, after an ancient philosopher who lived roughly 2,500 years ago, and who performed some of the earliest recorded experiments in optics, studying how light travels and how shadows form. It was a fitting name, because this satellite was about to carry the study of light further than anyone ever had. Micius was launched in 2016 by a team at the Chinese Academy of Sciences, led by the physicist Jianwei Pan, and it settled into an orbit about 500 kilometers above the surface of the Earth. Its purpose sounds almost simple when you say it plainly, and it is astonishing when you understand what it means. The satellite was built to distribute quantum entanglement between stations on the ground that were separated by distances no laboratory could ever hope to match. Here is what it did. Micius generated pairs of entangled photons, particles of light linked together in that fragile quantum way, and it sent one photon of each pair streaming down through the atmosphere to one ground station, and the other photon of the pair down to a second ground station somewhere else entirely. The two stations in Delinga and Lijiang were more than 1,200 kilometers apart. 1,200 kilometers. That is roughly the width of France and Germany laid side by side. That is the distance from London to somewhere far into the Alps, and the photons had to survive the trip down through the turbulent, weather-filled atmosphere, through cloud and air and all the noise of the real world, to reach the ground at all. And the entanglement survived. The correlations between the measurements at the two distant stations broke Bell's limit by more than 11 standard deviations. In the language of physics, 11 standard deviations means there is no ambiguity whatsoever, no reasonable doubt, no wiggle room for a skeptic. The connection between those two photons held across more than 1,000 kilometers of open sky. And the following year, the same satellite was used to establish a quantum-secured link between Beijing and Vienna, cities separated by more than 7,000 kilometers, the first intercontinental communication of its kind. The relationship between entangled particles, once established, does not weaken with distance and does not care about the space in between. Think for a moment about how hard this actually is, because the difficulty is part of the wonder. A photon is the smallest possible unit of light, and to keep two of them entangled you have to protect that fragile link from every kind of interference along the way. In the laboratory, over a few meters, that is already delicate work. But Micius was firing single particles of light from a moving platform 500 kilometers up, through the entire depth of the atmosphere, through the shimmer and turbulence and haze that make the stars twinkle, down to a telescope on a mountaintop, and catching them precisely enough to test the correlation between them. It is a little like standing on a fast-moving aircraft and throwing two coins to two people, standing on two different mountains 1,000 kilometers apart, and having both coins arrive exactly where they need to be, and then discovering that the way the two coins land is somehow coordinated, no matter how carefully you check. That it worked at all is a triumph of engineering. That the entanglement survived is a statement about the universe. The connection did not fray with distance. It did not weaken as the photons crossed all that turbulent air. It simply held, as if the 1,200 kilometers were not there. I want to make sure the lesson of this lands, because it is the beam that carries the whole rest of the night. Entanglement does not care about distance. Once two particles are linked, the connection between them is maintained no matter how far apart you drag them, with no field and no signal running between them to keep it alive. And entanglement, remember, is precisely the resource that quantum computation runs on. It is the thing the machine at the bottom of that cold refrigerator is exploiting when it computes, which means the resource these machines use is not bounded by the physical size of the hardware. It is not the kind of thing that has a single location at all. The relationship exists without any transmission. The connection persists without any messenger. Whatever holds two photons together across 1,200 kilometers of sky is the very same kind of thing the processor is using to think. Now, before we go on, I want to stop and simply sit with the image, because it is one of the most quietly overwhelming facts I know, and it deserves a moment of stillness. Picture two specks of light, born together in the belly of a satellite 500 kilometers above the Earth. Picture them being flung apart, one falling toward a mountaintop observatory in one province, the other falling toward a station more than 1,000 kilometers away. By every instinct you own, by every rule your body learned as a child reaching for objects in a room, those two specks are now separate things in separate places, and whatever once bound them should have been left behind up in the dark between them. It was not. Measure one, and the other answers in step across a gap wider than most countries, with nothing at all crossing the distance to carry the message. Feel how completely that dissolves the idea of distance. The universe is treating more than 1,000 kilometers as if it were nothing, as if the word apart were something that only means anything to creatures our size, standing on the ground, looking out at a world we were built to see as divided. Let yourself feel small here, but in the good way, the way you feel small standing under a clear night sky, not threatened, just standing at the edge of something far larger and far stranger than the room you are in. Because what that satellite proved, gently and decisively, is that the separateness we take for granted is not a feature of the world underneath. It is a feature of our view of it, and the machines humming in their cold cathedrals are quietly running on that indifference to distance, drawing on a connectedness that the universe apparently had all along, underneath the surface we mistake for the whole story. Two photons, a continent apart, and still, in some way our language barely has words for a single object. That is not a thought experiment. That is a satellite, an orbit, two mountaintops, and a result printed in the scientific record. Hold it next to everything else we have gathered so far, because we have now collected enough pieces that it is time to stop, lay them out on the table and look at the shape they make together. And the shape, I think you're going to find, is unmistakable. Part 7. Let us put the pieces together. We are about halfway through our journey now, and we have gathered a strange and beautiful collection of facts. So let us do something simple and useful. Let us stop climbing for a moment, catch our breath, and lay the pieces out side by side to see what they are trying to tell us together. Sometimes the individual facts are interesting, but the pattern only appears when you step back far enough to see them all at once. And I think the pattern here is about to become impossible to miss. Here is the first piece. The machine has to be hidden from the ordinary world in order to work. We saw this in the refrigerator, in the layers of gold and cold and shielding, in the fact that a single stray photon or a passing truck can destroy the computation. The quantum condition the machine relies on is so delicate that it can only survive in near total isolation from the warm local reality around it. That is piece 1, and I asked you to remember it, because it sounded at the time like nothing more than an engineering detail. Here is the second piece. What the machine is doing cannot fit inside the space it occupies, or even inside the entire visible universe. We saw this in the arithmetic, in that plain, brutal count where 300 qubits already involve more possibilities than there are atoms in everything we can see. The information the machine handles has, in the most literal sense, nowhere in ordinary space to live. It has no address. That is piece 2. And here is the third piece. The correlations the machine runs on do not respect distance at all. We saw this in the Bell experiments, in that cold corridor at Delft where two electrons agreed with each other across more than a kilometre, with nothing passing between them, and we saw it written across the sky by a satellite, 2 photons staying linked across 1,200 kilometers of open air. The resource these machines exploit is non-local. It is not the kind of thing that lives at a particular place. That is piece 3. Now look at them together. The machine must be sealed off from the local world. The information will not fit in local space. The connections it uses ignore distance entirely. 3 separate facts, gathered from 3 completely different directions, from cold engineering, from pure arithmetic, from decades of the most careful experiments ever performed. And they are all, every one of them, saying the same single thing. They are all saying that separation is not fundamental, that the division of the world into separate things sitting in separate places, with real empty distance between them, is not the bedrock of reality. It is a surface, and these machines are the first tools we have ever built that reach underneath it. I want to say that again, slowly, because it is the whole thesis of the night, and everything after this beat is simply going to deepen it. Separation is a surface, not the bedrock. The space between things, the distance you cross when you walk across a room, the private solidity of a single object sitting alone in a single place. All of it may be a kind of smooth skin the universe presents to creatures our size. Underneath that skin, the world appears to be something else entirely, something woven together in a way that has little to do with the distances your eyes report. And a quantum computer works, when it works, precisely because it does not do its computing on the surface. It reaches under, into the layer where here and there stop being the opposites we take them for. Once you see the pattern this way, the individual mysteries stop looking like separate puzzles and start looking like a single fact viewed from different angles. Why does the machine have to be so cold and so isolated? Because it is protecting something that does not belong to the local world, and contact with the local world drags it back to the surface and destroys it. Why can it handle more possibilities than there are atoms in the universe? Because it is not keeping those possibilities in the local matter of the chip. It is working in a space that is larger than the space we see. Why do its correlations ignore distance? Because distance, at the level where the machine operates, is not the real structure of things. The machine is not performing a magic trick against the rules of the world. It is quietly obeying a deeper set of rules that were always there, rules in which our tidy separations are the illusion, and the connectedness is the truth. And this reframes the question we have been chasing since the very first minute of tonight. We started by asking where the computation happens, and we treated it as a mystery about a missing location, as though the answer would be some hidden room we simply had not found yet. But maybe the question itself was slightly wrong. Maybe asking where assumes the very thing that turns out to be false, that the world is fundamentally a place of locations, of heres and theres, of addresses. If separation is only a surface, then where is a surface question? And the machine is doing something below the surface, in a layer where does not quite apply. So from here on, our path changes character. We have spent the first half gathering the evidence that reality is not local. Now we're going to spend the second half asking how far down that goes, and what, if anything, is at the bottom. We're going to look at answers we may never be able to check. We're going to look at why these machines get stronger as they grow. We're going to follow the boldest thinkers to the idea that space itself might be woven out of exactly the connectedness we have been describing, and that underneath even that, there may be nothing but information. Each step is going to take the same discovery, that separation is a surface, and push it one level deeper. And by the end, that sentence I gave you at the very beginning, the world is not where you think it is going to have earned its full and literal weight. Take a breath. Get comfortable again. We're going back down the staircase, and it goes further than you might expect. Part 8. The answers. We may never be able to check. There is a consequence of everything we have just seen that almost nobody talks about loudly enough, and it cuts at something human civilization has quietly leaned on since the very beginning of organized science. The problem is verification, and I mean that in the plainest possible way. We are building machines whose answers we may not be able to check. Think for a moment about what it means to check something. When an ordinary computer runs a calculation, you can verify the result in several ways. You can run it again. You can run a different method that arrives at the same answer by a separate route. In many cases, you can work backward from the output to confirm that it makes sense. The process is auditable. There is a chain of reasoning from the input to the output, and in principle, you can inspect that chain at every link. This is not a small feature. It is the load-bearing beam under all of empirical knowledge. Peer review works because results can be reproduced, proofs can be checked, claims can be tested by someone who did not make them. The entire enterprise of science rests on the quiet assumption that we can always, in principle, look inside the box and confirm for ourselves that what came out is right. In 2020, a group of researchers, including a computer scientist named Thomas Viddick, working at the California Institute of Technology, published a result in the theory of computation that has not received nearly the public attention it deserves. It is written in a line of dense notation that reads like alphabet soup, and I am not going to make you learn it. But I will tell you what it means, because what it means is quietly astonishing. The result concerns what happens when you let an ordinary verifier interact with two quantum systems that share entanglement. And what it shows is that entanglement gives you access to a class of problems that can be checked, which is immensely, incomprehensibly larger than anything an ordinary computer could ever verify on its own. As large, in fact, as the class of problems that are solvable at all, no matter how long they take. Sit with what that implies for these machines. As quantum computers grow more powerful, the answers they produce will increasingly lie beyond the reach of any ordinary check. A sufficiently large quantum computation will produce a result that no ordinary computer, no matter how enormous, no matter how long it is allowed to run, can confirm or deny. The computation becomes, from the point of view of the world you and I live in, an oracle, a black box. You put a question in and an answer comes out, and there is no independent way to know whether the answer is right. You cannot run it again in a way that checks it. You cannot cross-examine it with an ordinary method. The machine says the answer is this, and you either trust it or you do not. We are not fully at that point yet, and honesty requires me to say so. The machines that exist today are still small enough that their outputs can, at great cost, be spot-checked by ordinary means. But the trajectory is unmistakable. Willow already pushes into regimes where a full ordinary check is impractical, and the roadmaps of every serious quantum computing effort point towards systems where verification will become impossible long before the machines reach the applications people are most excited about. Drug discovery, materials science, the modelling of molecules too complex for any ordinary computer to simulate. These are exactly the problems where a quantum computer would be most valuable, and they are exactly the problems where we will least be able to check its work, because if we could check it with an ordinary machine, we would not have needed the quantum one in the first place. And this is not only an abstract worry for philosophers of science, it has teeth. Imagine a quantum computer used to design a new medicine, modelling the behaviour of a molecule far too complex for any ordinary machine to simulate. It hands you an answer. This molecule will bind to that target in this way, with these effects. If the answer is right, it could save countless lives. But you cannot check it the ordinary way, by simulating the molecule on a classical machine, because the whole reason you built the quantum computer was that the classical machine cannot do it. So how do you know? The gap between a correct answer and a plausible-sounding wrong one might not reveal itself until the medicine is already in human trials. Now imagine the same machines turned loose on financial models, on materials for aircraft, on the design of other machines, each time producing answers of enormous consequence that no independent classical check can confirm. We would be building a civilization that increasingly acts on the word of instruments it cannot audit. Not because anyone was careless, but because the answers come from a place we cannot follow them into. This is a new kind of trust, and we have not really reckoned with what it will mean to live inside it. This creates a genuinely strange situation for a species whose science has always been built on checking. We are going to have machines that can, in principle, solve problems of enormous practical importance, and we are going to have to trust their answers without being able to fully verify them by any independent route. The trust will have to be placed somewhere else, in the process, in the physics, in the theoretical framework that predicts the machine should work correctly. But here is the twist that folds this beat back into our central thread. The framework we would be trusting, quantum mechanics itself, is the very thing whose physical interpretation we cannot agree on. We are being asked to trust the output of a machine whose operating principle is a matter of active dispute, using a method that the civilization which built it cannot check. And notice why this is happening. It is not an accident, and it is not merely a limit of our engineering. It is another face of the same discovery we have been circling all night. The computation lives in a place we cannot enter to look. That is why we cannot check it. An ordinary computation happens somewhere we can inspect step by step on the surface of things, in the local world of separate parts. A quantum computation happens underneath that surface, in the non-local layer where the information has no address, where the correlations ignore distance, where the possibilities exceed the atoms in the universe. You cannot audit a process by standing outside it and rerunning it locally when the process is not local to begin with. The verification problem is not a bug. It is what it feels like from the inside to depend on a machine that reaches under the surface of the world. There is something almost vertiginous about this if you let it settle. For all of recorded history, the deal we made with knowledge was that we could, at least in principle, see how any answer was reached. We could trace the reasoning. We could stand behind the person who made the claim and watch them make it again. That is what separated knowledge from faith. And now we are building instruments that hand us answers from a place we cannot follow them into, reasoning we cannot retrace, a workspace we cannot enter. It does not make the answers wrong. The machines, as far as we can tell, work. But it does mean that our relationship to our most powerful tools is quietly changing into something new, something closer to consulting an oracle than to checking a sum. And the reason, underneath everything, is that the oracle is doing its thinking in a layer of reality that was never built for us to see. But I promised you honesty, and honesty means I also have to tell you the other half of this, because there is another face to these machines that only deepens the mystery rather than darkening it. Even as their answers become harder to check, the machines themselves are becoming more stable, more reliable, and the reason they are becoming more stable is, if anything, the single strangest thing in this entire story, because it should not be possible at all. Part 9. Local Hands. Protecting a thing with no location. Let us go back to Willow's strangest trick, the one I set aside earlier, because now that we understand non-locality, it stops being a puzzle and becomes a clue. Willow gets more stable as it grows. Add more qubits, and the errors do not accumulate. They cancel. The machine becomes more reliable the larger it gets. I told you this breaks every instinct we have about how complicated things behave. Now I want to show you why it happens, and why the explanation points straight back to the heart of our story. To make sense of it, you have to understand the problem it solves. Quantum states, as we have seen, are almost unbearably fragile. For decades, this fragility looked like it might make large quantum computers permanently impossible. The argument went like this: quantum states decay. Errors creep in constantly from the environment, and unlike ordinary data, you cannot simply copy a qubit to make a backup, because quantum mechanics forbids the perfect copying of an unknown quantum state. So there seemed to be no way to catch and fix errors before they piled up and destroyed the computation. The delicacy that makes these machines powerful also seemed to doom them. Then, in 1995, a physicist and mathematician named Peter Shor, whose name is going to come up again later tonight in a very different context, showed that quantum error correction was possible after all. His insight was subtle and beautiful. You cannot copy a qubit, and you cannot look directly at the quantum information without destroying it. But you can protect a single unit of logical information by spreading it across many physical qubits, and then you can make a very particular kind of measurement called a stabilizer measurement that tells you whether an error has occurred without ever telling you what the protected information actually is. You measure the relationships between the qubits, not the qubits themselves. You learn that something slipped, and where, without ever reading the delicate thing you're trying to keep safe. And because you only ever extract the error, and never the protected information, the fragile quantum condition survives. The error gets caught and corrected. The computation continues. Shor showed it was possible in principle. The question was whether real hardware could ever be good enough to do it in practice. That question was answered by something called the threshold theorem, which says that if the error rate of your individual physical operations falls below a certain critical value, roughly 1% for many designs, then adding more physical qubits to protect each logical one drives the error rate down and down and down as far as you want. Below that threshold, more qubits means more reliability. Above it, more qubits just means more total mistakes. The threshold is the tipping point, and for 30 years it hung in the air as a theoretical target nobody had reached. Willow, in 2024, reached it. As the team used more physical qubits to protect each logical one, the error rate fell exactly the way the theory said it would for a machine operating below the threshold, falling faster the bigger it got. Now here is the paradox that I want to sit with, because it is where the strangeness lives. Error correction works by making measurements, and measuring a quantum system, as we have said again and again tonight, generally disturbs it, causes decoherence, introduces errors. So you appear to be using a process that causes errors in order to fix errors. It sounds circular, even self-defeating. Why does it not simply make everything worse? The resolution is that the stabilizer measurements are carefully designed to extract only the pattern of errors and none of the protected information. They read the symptom without touching the patient. That is mathematically rigorous, and it works. But it only works cleanly under one condition. The errors have to be local, and they have to be independent. Each physical qubit has to fail on its own, in its own little corner, without its failure being secretly coordinated with the failures of others. And now watch what that means when you hold it next to everything else we know. The errors are local, the corrections are local. The whole error-correcting machinery operates on the assumption that noise is a local thing, hitting one qubit here, another there, each on its own. But the quantum information being protected is not local. It is entangled. It is distributed. It is spread across the qubits in that non-local way we have spent all night establishing, with no single address, with correlations that ignore distance. So the picture we arrive at is genuinely remarkable. You have local hands, catching local noise, successfully protecting a thing that fundamentally has no single location. Why can they? Why does local error correction manage to protect a non-local structure? And here is one honest reading, the one that threads this beat back into the whole. The structure the correction protects is more robust than any ordinary thing precisely because it is not tied to any one place. Local noise is a local attacker. A stray photon strikes here. A vibration arrives there. But you cannot destroy a thing by hitting a place if the thing is not, in the ordinary sense, at any place. To corrupt information that lives in the relationships between widely separated qubits, you would have to disturb many of them at once, in a precisely coordinated way, and random local noise almost never manages that. The information is safe not because it is shielded from the world, though it is, but because there is in a sense nothing local there for the local noise to grab. Remember the sentence from the very beginning. The machine has to be hidden from the world to work. We can now read it more deeply than we could then. The machine has to be hidden from the local world, because what it protects is non-local, and local damage cannot reach a thing that has no single location. That is why adding qubits stabilizes rather than destabilizes. Every additional physical qubit spreads the logical information a little more thinly across the non-local structure, makes it a little less anchored to any one vulnerable place, gives the local noise a little less to hold on to. In the ordinary world, more parts means more ways to break. But this is not the ordinary world. This is the layer under the surface, where the thing being protected does not live in the fragile local world where breakage happens. And so, uniquely among all the machines we have ever built, this one grows sturdier as it grows larger, because it is reaching into a place where the ordinary rules of fragility simply do not apply. There is a lovely irony buried in this that is worth drawing out. For decades, the fragility of quantum states looked like the fatal weakness of the whole enterprise, the reason large quantum computers might be forever impossible. Everyone assumed that non-locality, that strange refusal of quantum things to sit still in one place, was part of the problem, part of what made these states so hard to pin down and hold. But it turns out that the very non-locality that makes quantum information so slippery is also what makes it, once you learn to spread it correctly, so resilient. The thing that seemed like the weakness is the strength. A logical qubit spread across a non-local structure is harder to build and harder to control, yes, but once built, it is harder for the local world to destroy precisely because there is no single local place where all of it sits. Nature handed us a problem, and folded into the very same feature was the solution. The machine is not fighting against non-locality to stay stable, it is leaning on it. It is using the fact that the world does not keep its pieces in single places as the shield that protects the computation. And that is about as clean a demonstration as you could ask for that. These machines are not working on the surface of reality, where fragility rules, but underneath it, where the ordinary rules bend. We keep arriving from every direction at the same doorway. The information is real, it is usable, and it does not live at a place. And that raises a question so bold that when two of the most respected physicists alive proposed an answer to it, even they were careful to call it a conjecture. What if the reason entanglement ignores distance is that distance itself, space itself, is made out of entanglement? What if the connectedness is not stretched across space, but is the thing that space is woven from. Part 10. If entanglement is a thread of space itself. I have to slow down and put up a careful sign before this next stretch, because we are about to leave the solid ground of experiment and step onto the boldest, most speculative part of the whole night. Everything up to here has been measured, Bell's limit broken, entanglement across 1,200 kilometers, error rates falling below the threshold. Real, confirmed, published. What comes next is different. It is a conjecture. A brilliant, mathematically serious, widely respected conjecture proposed by some of the finest minds in physics, but a conjecture all the same. It has not been proven, and I am going to keep reminding you of that, because the idea is so beautiful it would be easy to forget. In 2013, two theoretical physicists published a paper with a title that reads like a tiny equation, ER equals EPR. The two of them were Juan Maldacena, one of the most cited physicists alive, and Leonard Susskind, another towering figure in the field. And to understand their claim, you need to know what those two little clusters of letters stand for, because it is a genuinely astonishing thing to set equal to each other. ER stands for Einstein and Rosen, and it refers to a paper they wrote in 1935 describing what we now call a wormhole, a bridge connecting two distant regions of space, a shortcut through the fabric of the universe. EPR stands for Einstein, Podolsky, and Rosen, and it refers to that other paper from 1935, the one about entanglement and spooky action at a distance, the very argument we followed earlier tonight. Two papers, the same year, one about bridges in space, one about the strange connectedness of distant particles. And Maldacena and Susskind proposed that these two ideas are not merely similar, they are the same thing. The claim is this: any two entangled particles are connected by a tiny microscopic wormhole, not as a metaphor, not as a loose analogy, as a literal description of the geometry of space-time. Entanglement in this picture is not a mysterious correlation stretched across an empty gap. It is a bridge, a thread of space-time itself joining the two particles, so short and so structured that it connects them directly, underneath the apparent distance between them. The reason the two entangled photons over China stayed linked across 1,200 kilometers is that, at the deepest level, they were never really 1,200 kilometers apart. They were joined by a thread that does not run through the space between them. It runs under it. Now, immediately, I have to close a door before you walk through it by mistake. These wormholes are not the science fiction kind. You cannot travel through them. You cannot send a signal through them. They are not tunnels for ships or messages. This is exactly why entanglement still cannot beat the speed of light, why the no-signaling theorem still holds. The bridge exists, but it is too small and too structured to carry anything across, so relativity remains perfectly safe. But the implication of the idea, even with that door firmly shut, is enormous. Because if entanglement is a thread of space-time, then space-time is not the fixed stage on which quantum events play out. Space-time is made of those threads. The geometry of the universe, the whole structure of near and far, of here and there, of distance and direction, would be produced by the pattern of entanglement among the quantum pieces underneath. More entanglement between two regions means they are more connected, woven more tightly together, closer. Less entanglement means the connection thins, and if you could remove the entanglement between two regions entirely, the geometric connection between them would not just weaken, it would come apart. The space between them would cease to mean anything at all. This is the idea physicists call emergent spacetime, the proposal that the three dimensions of space and the one dimension of time that we experience as the arena of everything are not the ground floor of reality. They are derived. They emerge from a deeper layer in which the meaningful quantity is not position, not distance, but entanglement, connectedness, relationship. Space is what a certain pattern of connection looks like from the inside, and that reframes everything we have been building toward. Non-locality suddenly stops being spooky at all. Of course, two entangled particles ignore the distance between them. The distance between them is itself just a shadow cast by their connection. The connection is the real thing. The distance is the appearance. I want to try to let you feel this gently, so let me ask you to do something with your mind. Look around whatever room you're in. Notice the ordinary distances, the gap between you and the far wall, the space between two objects on a table. You have always taken these for granted as simply given, as the empty container the world sits inside. Now imagine, just for a moment, that every one of those distances is not a given at all, but a woven thing, held together by countless invisible threads of entanglement, running between the tiniest pieces of the world, threads too fine and too numerous to see. The nearness of the far wall is not the absence of something. It is the presence of a dense weave of connection between you and it. Now imagine, softly, beginning to loosen those threads. As the entanglement between you and the far wall is removed, the wall does not move closer, and it does not move away. Something stranger happens. The very idea of how far loses its footing. The question of distance between you and the wall stops having an answer, because distance was only ever the shadow those threads were casting. Regions still richly connected stay near. Regions cut loose have no distance to one another at all, not a large distance, not a small one, simply no distance, because distance was never the fundamental thing. You're watching space itself dissolve back into what it might really be, a pattern of relationship, and the room you are sitting in reveal itself not as a container, but as a weave. And now, still inside that image, look down at the qubit on the cold chip and see it the way this picture would have you see it. It is not a lonely thing sitting at a lonely address, spinning out possibilities from one small location. It is a knot in the weave. When two qubits are entangled, a thread is drawn tight between them, and the more you entangle, the more of the loom you are working. So when the machine computes, it is not shuffling symbols around on the surface of space. It is reaching down into the weave and rearranging the threads, tightening some connections, loosening others, building temporary geometry out of the very stuff that space itself is made from. The reason the computation cannot be traced or checked from outside, the reason it has no ordinary location, would be that it is not happening in space at all, in the way ordinary things happen in space. It is happening one level down, in the loom, before space has fully been woven. That is why you cannot point to where. Where has not finished being made yet at the level the machine is working. Keep your footing, because this is wonder, not horror. Nothing in that image is a threat. It is the possibility that the most obvious feature of your existence, the plain fact of near and far, of being here and not there, is not the bottom of things but the surface of something more basic. And if that is true, then look what a quantum computer becomes. A quantum computer is a carefully woven network of entangled qubits. In this picture, when it computes, it is in some real technical sense building and rearranging geometry, threading and unthreading the connections from which space is made. The reason its computation cannot be simulated by an ordinary machine would be that the structure it moves through has no ordinary description, because it is more fundamental than the space an ordinary description is written in. The machine at the bottom of that cold refrigerator would be, when it runs, reaching into the loom where space is woven and pulling on the threads. I will say it one more time because I meant the warning. This is a conjecture. It connects quantum mechanics to gravity, two theories that have resisted being joined for a century, through the single idea of entanglement, and that is exactly why serious people take it seriously. But it is not proven, and it may not be the final word. Still, it points the same direction as everything else we have found. And it raises the obvious next question. If space is emergent, woven from entanglement, then what is the entanglement itself made of? What is the thread made of? Keep going down, and you arrive at a one-word answer that a great physicist spent the last years of his life trying to name. Part 11. The layer under the layer. If space might be emergent, woven out of entanglement, then the natural question is what the weave itself is made of, and the most influential answer to that question came from a physicist named John Archibald Wheeler. Wheeler was one of the towering figures of 20th century physics. He coined the term black hole. He worked on the earliest questions of nuclear physics. He was the doctoral advisor of Richard Feynman, and late in his life, in his 70s and 80s, he became consumed by a single question that he eventually distilled into three words that sound almost like a riddle, it from bit. Here is what he meant. Every physical thing, Wheeler proposed, every particle, every field, every patch of space-time, every property of every object in the universe, derives its existence from information. Not information in the loose, everyday sense, but in the strict sense, the sense of yes or no answers, of distinctions, of definite responses to definite questions. In Wheeler's picture, the universe is not made of matter and energy that happen to carry information along with them. The universe is made of information, and matter and energy are what information looks like when it takes on physical form. The physical thing, comes from the bit, the fundamental distinction. Reality, all the way down, is not stuff. It is answered questions. Now, this could sound like pure philosophy, the kind of grand speculation that feels profound at midnight and evaporates by morning. But it is not only philosophy, and here is the experimental thread that keeps it honest. In 1961, a physicist named Rolf Landauer, working at IBM, proved something surprising about information. He showed that erasing a single bit of information, resetting it from an unknown state to a known one, must release a tiny, specific minimum amount of heat. This is called Landauer's principle, and it sounds like a dry technical footnote, but think about what it says. It says that information is not just an abstract description we lay over the physical world from outside. Erasing information has a real, physical, thermodynamic cost. It generates heat. Information, in other words, is a physical thing subject to physical law. For 50 years, this was considered too small an effect to measure directly. Then, in 2012, an experiment in Lyon, France confirmed it. Researchers measured the minuscule burst of heat released when a single bit was erased, and it matched Landauer's prediction exactly. Information is physical. It has a thermodynamics. It is woven into the fabric of the real. There is one more piece to lay alongside this, and it comes from the study of black holes, of all places. In the 1990s, work by a series of physicists established something now called the holographic principle. It says that the maximum amount of information you can pack into a region of space is not proportional to the volume of that region, as you would naively expect, but to its surface area, to the size of the boundary around it. It is as if everything happening inside a three-dimensional region could be fully described by information written on its two-dimensional surface, the way a hologram stores a three-dimensional image on a flat piece of film. The sharpest version of this idea, developed by Juan Maldacena in 1997, is now the most precisely tested relationship of its kind in all of theoretical physics. It says, in effect, that a three-dimensional world with gravity can be exactly equivalent to a quantum system living on its lower dimensional edge. The volume is, in a real sense, a projection of information on the boundary. It is worth pausing on how strange that holographic idea really is, because it inverts something we never think to question. Your whole life, you have assumed that the contents of a space are held inside its volume. A room holds what it holds because there is room inside it. A box contains its contents in its interior. But the holographic principle says that the true information limit of any region is set by its boundary, by the area of the surface wrapped around it, not the volume within. It is as if the inside of everything is, in the deepest accounting, written on the outside. The three-dimensional fullness we live in, the sense of depth and interior and enclosed space, would be a kind of projection, a reading out of information stored on a lower dimensional edge. This is not a fringe notion. It emerged from trying to understand how much information a black hole can swallow, one of the most carefully reasoned corners of modern physics, and its precise mathematical form has passed test after test. And it says quietly that the volume you think you live inside is not where the information of the world is really kept. The interior is the hologram, the edge is the ledger. Put all of this together and something clicks into place about our machines. If matter is information, if space is woven from entanglement, and entanglement is a form of information, if the structure of reality at its deepest level is the processing and encoding of distinctions, then a quantum computer is not a tool that processes information about reality from the outside. A quantum computer is a piece of reality doing what reality does at its most fundamental level. It is information processing information. It is, in a phrase that stops me every time I say it, the universe computing itself, using a small piece of itself that we happen to arrange for the purpose. And this finally cashes in a phrase I asked you to remember, hours ago now, back when it sounded like a problem. Do you recall the arithmetic when we found that the information inside a quantum computer had nowhere in ordinary space to live, no address? At the time, that homelessness felt like a paradox, a difficulty, a thing that ought to worry us. Now look at it again through this new lens. Of course the information has no address in ordinary space. Ordinary space is not where information lives. Ordinary space is a thing that emerges from information, a surface it projects, a shadow it casts. Asking for the information's address in space is like asking which of the pixels a photograph is really stored in, when the whole photograph is the pattern, not any one place. The no address that seemed like a flaw turns out to be pointing straight at the truth. The information has no address in space because information is more fundamental than space. It is the ground floor. And these machines run close to that ground floor, closer than anything else we have ever built, which is exactly why they can reach into a space larger than the universe, why they ignore distance, why they grow stronger as they grow. They are not operating above the substrate of reality, the way every ordinary machine does, pushing symbols around on the surface. They are operating in it. I want to keep the honesty flag flying here, because this is interpretation, not settled fact, and I would be doing you a disservice to pretend otherwise. Nobody has proven that information is the true ground floor of the universe. It from bit is a hypothesis, a direction, a suspicion held by some very serious people, not a theorem. But notice once again that it points the same way as everything else. The refrigerator, the arithmetic, the Bell tests, the satellite, the error correction, the emergent space conjecture, and now this. Every single one of them from a completely different direction keeps saying that the world of separate things at separate addresses is not the bottom. There is a layer underneath, made of connection and information, where separation does not apply. And there is one more machine being built right now, along a different road from Google and IBM, that expresses this idea more purely than anything else we have seen. It stores its information not in a place, but in a relationship, and it is named after a man who vanished. Part 12. Information hidden in a relationship. Every quantum computing company on Earth is fighting the same war, and the enemy is the universe itself, the constant pull that drags fragile quantum states back to the surface and destroys them. Google and IBM fight that war with brute craftsmanship and elegant mathematics. Build the best qubits you can, get the physical error rate as low as possible, and then layer quantum error correction on top to catch the mistakes that remain. It is working, as Willow proved. But there is a company that has spent more than 2 decades betting on a completely different strategy. A strategy that does not try to catch errors after they happen, but to make the errors nearly impossible in the first place. That company is Microsoft, and the physics behind its approach is the purest expression of everything we have been circling all night. Their approach centers on an exotic object called a Majorana zero mode, and the name carries one of the strangest and most haunting stories in the history of physics, so let me tell it, because the man and the physics rhyme in a way I have never quite been able to shake. Ettore Majorana was an Italian theoretical physicist born in 1906, and he was regarded, even by the standards of a generation that included some of the greatest minds who ever lived, as a genuine prodigy. Enrico Fermi, who worked alongside him, and who was no stranger to genius, once compared Majorana to Galileo and Newton, placing him among the small handful of people who come along once in centuries. In 1937, Majorana published a paper proposing that certain particles could be their own antiparticles. In ordinary physics, every particle has a mirror image antiparticle, an electron has its opposite, and when the two meet they annihilate. Majorana proposed that some particles might be perfectly symmetric, equal to their own mirror image, neither quite particle nor quite antiparticle, but somehow both at once. It was a subtle, elegant, profound idea. And then, in March of 1938, at the age of 31, Ettore Majorana boarded a boat travelling from Palermo to Naples. He was seen aboard by other passengers, and he was never seen again. No body was ever found. No certain explanation was ever established. He withdrew a large sum of money, wrote a few strange notes, stepped onto a ship, and vanished from the world entirely, leaving behind an idea and a mystery and nothing else. His physics survived him. His fate did not. Nearly 90 years later, we still do not know what happened to him. The objects that now carry his name, Majorana zero modes, are not quite the particles he originally described. They are what physicists call quasi-particles, collective patterns of behavior that can emerge in certain specially engineered materials, called topological superconductors, under just the right conditions. But they share the crucial mathematical property, and more importantly, they have a feature that makes them extraordinary for computing. A Majorana zero mode cannot exist alone. It always comes in a pair, and the two members of the pair are separated in space, held apart from each other. And here is the thing that matters, the thing that is the whole point. The quantum information they encode, the actual logical state of the qubit, is not stored in either one of the two modes. It is stored in the correlation between them, It lives in the relationship, not in the members of the relationship. Neither mode, on its own, holds the information. Only the two of them together, only the connection between them holds it. Now feel how directly that expresses everything we have been building toward. If the information lives in the relationship between two separated places, and not at either place, then a local disturbance cannot destroy it. A stray photon landing on one mode cannot corrupt information that is not stored in that mode. A vibration reaching one location cannot flip a bit that is not located there. To damage the information, you would have to disturb both widely separated modes at once, in a precisely coordinated way, and the random noise of the environment essentially never manages that. The qubit is not shielded from the world in the ordinary sense, wrapped in armor. It is hidden from the world in a far stranger sense. There is no single place where it is, and so there is no single place where the world can reach in and touch it. Physicists call this topological protection, and the word topological refers to properties that are global rather than local, properties of the whole shape rather than any particular point of it. The classic image is the difference between a sphere and a donut. A sphere has no holes, a donut has exactly one, and no amount of gentle squeezing, stretching, or bending, short of actually tearing the material, can turn one into the other, because the number of holes is a property of the entire object at once, not of any single spot on it. You cannot change it by poking one place. You would have to rip the whole thing. Topological qubits store information the same way, as a global property that local damage cannot reach. In February of 2025, Microsoft announced a chip they called Majorana 1, describing it as a first demonstration of topological qubits reliable enough to serve as a computing platform. And I have to give you the honest picture here, because the field's reaction was a careful mix of genuine excitement and well-earned caution, and both halves are true. Microsoft has been chasing this for over 20 years, and along the way an earlier experimental claim in this area had to be retracted in 2021 after errors were found in the analysis. So the community has learned to be patient before it celebrates. The 2025 announcement was more carefully documented, but independent verification was still underway. The honest verdict is that it looks promising, and it is not yet confirmed to the standard the field demands, and the history of this particular quest counsels patience. If it works, it could shorten the road to useful quantum computing by an enormous margin, because a topological qubit might need far fewer physical components to protect each logical one. But whether or not this specific chip is the breakthrough, notice the shape of the idea itself, because the shape is what matters for us, and the shape does not depend on which company wins the race. Information that is real, readable, and usable, and yet has no location, because it lives in the relationship between two places rather than at either of them. Do you hear it? That is the same shape as everything else tonight. It is the same shape as the computation with no address, the same shape as the correlations that ignore distance, the same shape as the many worlds picture, where the information is distributed and non-local, the same shape as emergent space, where connection is more fundamental than location. Over and over, from the arithmetic to the satellite to the error correction to this, the world keeps telling us the same thing in different accents. The most protected, most fundamental information there is does not live at a place. It lives in a relationship, and I cannot leave this beat without sitting for a moment with the man himself, because there is a quiet rhyme here that I find genuinely moving. Ettore Majorana was, by the accounts of everyone who knew him, one of the most gifted minds of his century, and one spring night he stepped onto a boat and out of every place in the world, leaving no trace, no location, no answer, nowhere anyone could point to and say, there, that is where he went. And nearly 90 years later, machines are being built around the ghostly objects that bear his name, and the entire point of those objects is that what matters about them is not where they are, but how they are related. That the thing worth protecting lives in a connection, not a location. A man who vanished from every place, lending his name to a kind of information that was never in any place to begin with. I do not know what to do with that except to notice it, and to let it sit, and to feel how strangely the physics and the life seem to be telling the same story. The important things, it keeps turning out, are not always somewhere. Sometimes they are in the space between, in the relationship, in the connection that has no address at all. Part 13. 3 doors, all of them strange. We have gathered everything now, and it is time to be honest about what it does and does not tell us, because the worst thing I could do at this point is sell you a tidy answer, that the evidence does not actually support. We have established beyond serious dispute that reality is not local, that separation is not the bedrock, that these machines work by reaching under the surface of the world into a layer where here and there stop meaning what they mean to us. That much is solid. But when you ask the deeper question, what exactly is that layer and how far down does it go, you arrive not at a single answer, but at a set of doors, and honesty requires walking you past all of them, rather than shoving you through the one I happen to find most beautiful. The first door is the possibility that quantum mechanics, as we currently have it, is incomplete. That there is a deeper layer of physics, not yet discovered, that would explain all of this strangeness in more familiar terms. That the non-locality is real, but will someday be accounted for by some mechanism we have not yet found. And the enormous space of possibilities is a feature of our mathematics rather than a literal description of the world. This was Einstein's hope, and I have real sympathy for it, because it is the most conservative option. But it is also the door that the experiments have made hardest to walk through. The loophole-free Bell test slammed it nearly shut. Any replacement theory would have to reproduce every prediction quantum mechanics makes, while ruling out the local hidden variables the experiments already killed, and after decades of trying, no one has built such a theory. The door is not locked, but the evidence is leaning against it with tremendous weight. The second door is the possibility that quantum mechanics is complete and correct, and that reality genuinely is non-local and non-classical, exactly as the theory taken at face value describes. That superposition, entanglement, and the space larger than the universe are real features of the world, not artifacts of our notation. That when a quantum computer runs, it genuinely draws on resources no single ordinary universe can provide, and that David Deutsch and Hugh Everett were, in the most important sense, right. This is the door the evidence most directly supports if you simply take the mathematics at its word. It is also the most disorienting, because it asks you to accept that most of reality is permanently hidden from you, running in parallel or woven into a structure you can never fully see. This is the door behind which the multiverse lives, and I want to be precise about its status. The many worlds picture is one honest reading of this second door. It is bold, it is serious, it is held by real physicists, and the behavior of these machines is consistent with it. But it is an interpretation, not a proven result, and the machine does not distinguish it from the alternatives. This is why, all night, I have refused to tell you that quantum computers prove the multiverse. They do not. They are consistent with it. That is a very different and much more honest claim. The third door is the possibility that the truth is something genuinely new, a physics that is neither ordinary nor quantum in the sense we currently mean, a framework that would resolve the old measurement problem and tell us cleanly and unambiguously what is really happening when one of these machines runs. Most working physicists, if you press them, would quietly prefer this door, because it is what science usually does. When the existing frameworks strain, you build a better one. But there is no agreed candidate, no proposal that most physicists accept as the answer. The measurement problem is more than 60 years old, and no closer to resolution than the day it was named. The interpretations multiply and none commands consensus. So the third door stands open onto a room we cannot yet see into. I want to dwell on why physicists cannot simply run an experiment to settle which door is right, because it gets at something important about the limits we are pressing against. The trouble is that all three doors predict the same laboratory results. They have to, because the laboratory results are just quantum mechanics, and quantum mechanics is not in dispute. What is in dispute is the story underneath the mathematics, the picture of what the symbols mean, and every one of these pictures reproduces the same numbers on the same dials. The many worlds reading, and a future replacement theory, and some undiscovered new physics could all, in principle, give you exactly the entanglement correlations we measure, exactly the below-threshold error rates we see, exactly the sampling results Sycamore produced. So there is no single experiment you can run that makes one door light up and the others go dark. That is a genuinely unusual situation in science, where normally you resolve a dispute by finding the measurement that separates the rivals. Here the rivals are, at least so far, experimentally identical and only differ in what they say reality is. It is possible that will change, that someone will find a clever test that pries the doors apart, and there are physicists working on exactly that. But it is also possible that the question of which story is true sits, at least for now, just past the edge of what measurement can reach, in a place where only the mathematics can go, and the mathematics is silent about meaning. 3 doors. And here is the honest heart of it. We do not know which one is real. The machines do not tell us. They work, and their working is consistent with more than one story about why. And choosing between those stories is beyond anything we can currently measure. That undecided state is not a failure of the video to reach a conclusion. It is the actual condition of the science, and I would rather hand you the real uncertainty than a false certainty dressed up to sound impressive. There is one more idea worth a brief, careful pass, because people always ask, and because it genuinely does look different in the light of everything we have covered. It is the old question of whether we might be living in some kind of simulation. Set aside the science fiction version for a moment, and look at what quantum computing actually adds to the question, because it is not what most people expect. Back in 1982, Richard Feynman pointed out that an ordinary computer cannot efficiently simulate a quantum system. The cost explodes exponentially, for exactly the same reason we found when we counted qubits. This means that if our universe contains genuine quantum mechanics, and every experiment says it does, then any machine capable of simulating a universe like ours could not be an ordinary computer. It would have to be a quantum one, or something with equivalent power, and a quantum substrate is not a simpler, tamer, more familiar thing than the reality it produces. It would be at least as strange, at least as non-local, at least as bound up with the mysteries we have spent tonight exploring. The point is not that we are simulated. I am not claiming that, and the evidence does not support it. The point is subtler, and, to me, more beautiful. Whatever might be underneath our reality, if anything is, cannot be something cozier and more ordinary than what is on top. The strangeness does not go away when you move up a level. It reproduces itself. There is no comfortable classical bottom to fall back to. We have looked, and it is not there. And lest all of this float away into pure metaphysics, let me anchor it firmly back to the ground, because there is one place where these ideas are already reaching into your daily life, quietly, right now. The security of nearly every private message, every banking transaction, every sensitive communication on Earth rests on a kind of mathematics that is hard for ordinary computers to crack. But in 1994, that same Peter Shaw we met earlier devised a quantum algorithm that could, on a large enough quantum computer, break that mathematics wide open, factoring enormous numbers in hours instead of the age of the universe. A machine capable of running it at full scale does not exist yet, and is likely at least a decade away, requiring millions of physical qubits. But the threat is taken so seriously that between 2016 and 2024, a global effort ran to design new codes that even a quantum computer could not break, and those new standards are being deployed across governments and banks as we speak. The reason for the urgency is a strategy with a chilling name: harvest now, decrypt later. Hostile parties can record encrypted traffic today, store it, and simply wait, knowing that when a large enough quantum machine finally exists, they will be able to unlock everything they have been quietly collecting. So the non-locality we have been exploring, the strange underlayer of the world, is not only a philosophical curiosity. It is already reshaping the machinery that keeps your secrets, precisely because everyone who understands the field believes these machines are going to be able to reach places ordinary machines cannot. The metaphysics and the mortgage payment turn out to be connected after all. 3 doors, all of them strange. A simulation question that only deepens rather than dissolves, and a very ordinary padlock already being quietly replaced because of what these machines can touch. We are almost home now. There is only one thing left to do, which is to stand back from all of it and ask what it means that we built such a thing at all, before we fully understood what we were building. Part 14. The world is not where you think it is. There is a long and humbling tradition in the history of science of tools running ahead of theories. We used fire for something like 300,000 years before we understood the chemistry of combustion. We built bridges and cathedrals for millennia before anyone could write down the mathematics of why they stood. We developed anesthesia and put people gently to sleep for surgery before we understood the first thing about how it silences the brain. In every one of these cases, the practical ability came first, and the understanding limped along behind, arriving years or centuries later, changed forever by the existence of the thing that worked before anyone knew why. The tool teaches the theory, not the other way around. Quantum computers are the newest entry in that ancient tradition, and they may be the most extreme one we have ever encountered. We built them, they run, and we do not know, not with confidence, not with consensus, not with any single picture that all physicists agree on why they run. We do not know where the computation happens. We do not know what part of reality is hosting the information. We do not know whether the parallel branches are real, or whether space is genuinely woven from entanglement, or whether information is the true flaw of the world, or whether we have built the first instrument that reaches down and touches a layer no human sense was ever meant to touch. What we know is that the machine works, and that the question of why it works, the real why, the one that would require a complete and satisfying picture of what reality actually is, remains open. Not just open in the philosophy books, open in the laboratory. There are experiments being designed right now in the United States, in China, across Europe, probing the relationship between entanglement and the geometry of space, testing the boundaries of these ideas, trying to see a little further into the layer under the surface. The answer is not here yet, but the question has never been more sharply posed, and the machines that are posing it grow more powerful every single year. Let me gather the whole night into one thread, one last time, and then I will let you rest. We started with a machine that finished in 200 seconds what should have taken 10,000 years, and I told you the strangest thing about it was not the speed, but the missing where. We went to the coldest place we have ever built, and found that the machine has to be hidden from the world in order to work. We did the arithmetic and discovered that what the machine handles cannot fit inside the entire visible universe, that the information has no address in ordinary space. We met a man who concluded 40 years ago that space was simply the wrong place to look, and then we found the hard experimental proof beneath all of it. The universe does not compute locally. Separation is not the bedrock. A satellite held two particles together across 1,200 kilometers of open sky. Local hands protect a thing with no location. Space itself may be woven from connection, and under the connection there may be nothing but information, and the most protected information there turns out to live not in a place, but in a relationship. Every thread, from every direction, pulling toward the same center. And the center is this: the separateness of things, the space between them, the distance you cross when you walk across a room, the private solidity of a single object sitting alone in a single place. All of it may be a surface. A smooth skin the universe shows to creatures our size, built by evolution to track objects and dodge predators and reach for fruit, never built to see the layer underneath, where here and there are not the opposites we take them for, where the world is a single connected structure of relationship and information. Quantum computers are the first machines that work by reaching under that skin. That is what they revealed. Not that they are fast, not by themselves that there are other universes, though there may be. What they revealed is quieter and larger than either. They revealed that the world was never built the way our eyes insist it is. So here, at the end, is the sentence I gave you at the very beginning, and I hope you can feel how much weight it has gathered along the way. The world is not where you think it is. When I first said it, it was almost a tease, a hook, a promise I had not yet earned. Now I mean it as literally as I have ever meant anything. The where of things, the separation, the distance, the address, is the surface. It is the part your senses hand you, the part that lets you live an ordinary life among ordinary objects. And underneath it, the world is not divided the way it looks. The far wall and the near chair, the two entangled photons over China, the qubits spread across the cold chip, are all part of something that does not keep its distant pieces truly apart. We did not set out to discover this. We set out to build a faster computer. We got that. But we also got, without quite meaning to, a window into something that has no settled name, no agreed interpretation, no comfortable explanation. In refrigerators colder than the space between the galaxies, we are running computations that touch more possibilities than there are atoms in the sky, and we're doing it right now, tonight, while you drift towards sleep. The machines are running. The answers are real, and whatever they are reaching into when they compute, it is not nothing. You can hold this as something frightening if you like, and there is a version of it that is. The most powerful tool we have ever built runs on principles we cannot fully explain, drawing on resources we cannot locate, in a layer of reality we cannot directly see. That is a reasonable thing to find unsettling. But there is another way to hold exactly the same facts, and it is the one I would leave you with as the room goes quiet. It is the particular kind of wonder that comes from standing at the true edge of what is known, and feeling the ground there not as solid but as open. Every generation believes it lives at the frontier of knowledge, and most generations are wrong, their mysteries later dissolving into ordinary explanations. But every so often, rarely, genuinely, human beings stand in front of something that does not fit, something that refuses to reduce to the familiar, something that insists on being taken on its own strange terms. This is one of those times. We built a machine that only works because the world is not what it appears to be, and in building it, we caught the world in the act of being something deeper than a collection of separate things. Sleep on this if you can, and let it be a soft thing rather than a sharp one. We are the first generation of human beings to hold a tool that only works by borrowing from a layer of the world our ancestors never suspected was there. Every person who ever lived before us looked out at a world of separate objects at separate distances and took that separation to be the final truth of things. We are the ones who got to build the small cold machine that quietly says otherwise. That is a strange and rare privilege, to be alive at the exact moment a hidden seam in reality begins to show, and to be able to feel the wonder of it without needing to have the answer yet. The answer is not the gift. The question is the gift. The distance between you and everything you love feels so real tonight. The space around you feels like an empty container, and the objects in it feel solid and apart and alone. That is the surface, and it is a good and necessary surface, and you are allowed to live on it. But somewhere underneath, if these machines are telling the truth, none of it is quite as separate as it seems. The world is not where you think it is. It never was. And the strangest, most patient, most beautiful part of all of this is that we found out not by looking up at the stars, but by building something very small and very cold, and asking it a question, and listening very carefully to what it said back.